My name is Greg Hoglund, and this is James Butler. This is actually Jamie's talk, so I'm just going to give a little introduction and then turn it over to Jamie. He did all the technical material here, but I just wanted to say a little thing about Jamie. He goes by Fuzanop on rootkit.com, and I met him about a year ago, and he impressed me a great deal with the release of the FU rootkit. And he implemented a rather new technique called direct kernel object manipulation. For a Windows rootkit, he had to do a great deal of reverse engineering to be able to figure out how those directories or those structures in memory work. So he's not only a very good reverse engineer, his code is also very clean. He pays a great deal of attention to quality. And this impressed me to the point where I had to fight off a couple of other companies to try to hire him, but he finally chose HB Gary and started working for us in January. And I also want to point out that this is entirely his personal choice to wear a tie. I did not force him to do that. So Jamie's elite. Turn it over to him.
Thanks. Okay, so today we're going to discuss a freeware tool called Vice that will catch hookers. And mainly the motivation for writing this tool was to find user mode rootkits that hook API calls and so forth. And to also convince the people at rootkit.com to stop writing userland rootkits because they're sort of lame. So here's a quick agenda. We have a lot of slides to cover. I hope I can get it all in because the Vice stuff is new, plus I'm going to cover some advanced rootkit stuff. So if you're in the room just because you want to learn about defense, I'll give you a little bit of that, but my main areas of research are more offensive in nature. So I have to show you the FU rootkit. So quick overview of this operating system design. You probably all know this if you've programmed in Windows at all. There's the userland portion that kernel32.dll and ntdll. These expose the kernel level functionality to the Win32 API. You can use these in programming to request operations of the kernel. So once you get into kernel mode, these are where the low-level functions are actually implemented. The kernel keeps track of processes, files, or open files, I should say, ports, and so forth. So the kernel has all this memory objects. It keeps in memory that keeps track of like privileges and so on and so forth for accounting purposes. So when your nice little task manager requests, hey, give me a list of the processes that are running, it goes through kernel32 and then ntdll and then it hits kernel. So typical attack scenario is an attacker will gain elevated privilege once. After that, we're not going to talk about gaining elevated privilege. There have been some talks about that. The Metasploit talk was good, and you all know about zero-day attacks. But once you gain access to a system once, you want to be able to come back, and you don't want to keep exploiting the box over and over. So an attacker will put down a rootkit to hide their presence and their activity on the box from system administrators and so on and so forth, and maybe IDSs. So your rootkit is acting as part of the operating system if it's intercepting API calls. It's really part of the operating system if it's down in the kernel. So this is a brief overview of the state of rootkits. In the past, probably the early 80s or whatever, we saw a lot of trojaning of binaries on disk with like the PS and so on and so forth. And this has been sort of solved in today's market with Tripwire and a bunch of other different vendors. They look for changes on the hard drive itself and maybe changes in the environment path or whatnot. So a more advanced rootkit, which for Windows, Greg wrote the first Windows NT rootkit to filter these API calls, and he did it in the kernel by hooking the system call table. This way you could totally bypass checkers like Tripwire and so forth that were just looking at disk. So within the kernel you can hook the system call table, you can hook the interrupt descriptor table on older versions of the operating system. You can also hook the import address table, and I'll talk about that in a moment. So here's just a quick overview of the import address table. When your process starts up, it relies upon other DLLs in the Windows environment. And those DLLs, your process maybe did not write those, but it has to import the functionality. So it keeps a table of where the actual function is that it's going to use, and the loader sets up this table for you. So you just say, okay, I want to use create file ex, and then the loader will put the appropriate address of that function from the kernel 32 DLL into your import address table. And this is just a blow up here. These functions are either exported by name or by ordinal, and the number there is just a dummy number representing the function address. So normally what would happen is the code in the program that's written, say Task Manager, would then jump through the import address table. From the import address table, it would go follow this path to kernel32.dll or whatever. Well, you see here that we have some rootkit injected into the process address space. It's represented by the red bad code. And we hook the import address table. So all we have to do is change one D word. And you can't really use memory protections and so forth because this import address table needs to be written too. A more advanced rootkit would go into the kernel. Kernel32.dll eventually calls ntdll, which eventually calls through the system call table, and that's what's represented here. It goes to chaos system service, which takes the system call number and eventually calls through the system service descriptor table, or the system call table in the kernel. Each entry in this is a blow up here. Each entry is just a function pointer to find the address of the function in question. So here's normally what would happen. The application makes a system call, goes to the system call table, and then goes to the appropriate function within NTOS kernel. Again, we have a rootkit in memory. We only have to patch one D word, and we can alter the control path of the application. And by doing this, we can intercept calls and filter out data so that our processor, so on and so forth, is not displayed. Now, a more advanced technique is to hook inline. So it's sort of easy to check the system call table to see if it's hooked. But you can also patch, do inline function patching, also called detours. And what you do there is you put a jump in the target function to jump to your bag code, and then eventually your rootkit would call back into the good function. This is a bit tricky to do correctly. Greg's written a rootkit that'll do it. And also all the HIPS vendors seem to do this a lot. So just quick animation of this process. Task Manager, whatever. Maybe this case it's Explorer. We create a file. So kernel32.dll runs for a bit. Create file W is the function in question here. It calls into ntdll. Notice there's a different export name there. It's nt create file at this point. It runs for a bit. Then it jumps into kernel mode. In kernel mode, in this case, we're going through the interrupt descriptor table. You don't have to do that on your versions of the OS. You can use the more advanced fast calling mechanism from the Intel architecture called sysenter. But regardless, if you don't go through the IDT, you'll still go through the system call table, even with sysenter. So it'll contain the address, the true address in the kernel of nt create file, which is in NTOS kernel. You could also hook here, I don't demonstrate in the slide, but you could overwrite those first couple bytes with the immediate jump. So, Vice is a tool that will try to detect hooks. We say it detects rootkits, but they're only part of the things that hook. There's legitimate hooking that's done by Microsoft themselves to redirect execution. A lot of your personal firewalls and other HIPS products will hook. So just because it detects a hook, it may not be a rootkit. Vice was written more or less, it has API that could be incorporated into other tools, such as a full-blown IDS application. So we'll try to do a demonstration here to see if it works. Although the demo gods have not been happy at Black Hat this year. So what I'm going to run here is, it's not a rootkit because I'm not going to rootkit my own box. This is a TDI-Mon from sysinternals, and it hooks, it has an interesting hooking technique. I should explain what all Vice is looking for. Vice looks for hooks in the import address table of every process. Vice also looks for immediate jumps of all those functions. So if you put a jump to some bad code within an exported function of a DLL, Vice should catch that. Vice will look at the system call table, look for jumps that are outside of NTOS kernel because they're obviously hooks. Then it will follow all those functions and analyze the first few bytes looking for jumps there using the detour trick, looking for rootkits that use the detour trick. Then it will also go to individual device drivers that you can specify. There's a driver.ini file that comes with Vice. It has a few devices that are listed. Excuse me. What it'll do is every device driver has a table that manages requests. They're called ERPs. So there's a major function table that you can hook. Not many rootkits do this yet, but you can achieve a lot of the same functionality of a rootkit just by hooking these ERPs. So you could hook tcp/ip.sys and watch for calls to, hey, give me a list of the open ports. You could hook at the ERP level and filter data. I don't think I've seen a publicly available rootkit that does that, but it's completely possible. And sysinternals tool TDI-Mon happens to hook at that ERP level within tcp/ip.sys. So this is the Vice tool starting up. Greg wrote the GUI and helped me with some of the debugging. It uses the .NET framework, which is free from Microsoft. So if you, Vice came on your conference proceedings. If you try to run it and you get some crazy error, it's probably because you don't have the .NET framework installed. And you can download it for free from Microsoft. I think it's about 28 meg though. So we just click scan. The progress bar advances as it goes through each process. If you've looked at Vice before on rootkit.com, this is a totally new version, it hasn't been released yet, and I fixed the bugs. So in the top window you see there, that's looking for user mode hooks. And kernel 32 is being hooked a lot of places by NTDLL. Obviously, this is probably just a false, it is a hook, so it is detecting it, but it's not a malicious hook. So you don't have to worry about it, especially if you have some kind of file integrity turned on in the WinNT system32 directory. You don't have to worry about that NTDLL being like a replacement NTDLL. Notice that Vice will also tell you the full path, if it can, where on the file system the hook is, so you can delete it if it is malicious. In the bottom, in the bottom window is the list of the ERPs it found hooked. It also lists the hook address, so you know where to go look in memory. If you had WinDebug or some other kernel debugger running, soft ice, etc., you could unassemble the instructions that are at that address and you could try to glean what the rootkit was doing. Again, it lists out where on the file system the hook is, so in this case it's tdi.msys.sys. If you look at the About button, there's different little icons. They're just, again, to poke a little bit at the rootkit community to try to get them to do better. The ERP hook is difficulty level medium, and it has that little orb connection type of icon. System call hooking is kind of easy now. It gets a little bit more advanced if there's memory protections enabled on the system call table, but they're really easy to turn off. And there's been a lot of people that have talked about that, including myself and some other hackers that use a different technique. If you do inline function patching, that's sort of hard because you have to disassemble the first few bytes of the function because you don't want to cut on a uneven instruction boundary since the x86 has a variable length instruction. And then if you hook in the IAT, we have a little Elmer's glue bottle because that's just really lame. So that was Vice. Here's some snapshots of real live rootkits that was taken from one of our VMware machines. Here's Vice versus Hacker Defender, which is pretty popular and extremely advanced. The gentleman also contributes occasionally to rootkit.com, and he's pretty knowledgeable. Here's Vanquish. It does a lot of API hooking up in the user land. You can see, it may be small for you, but I think it's in some of the slides. It hooks kernel32.dll a lot. It looks for create process W, etc. And what it's trying to, every time you try to create a process, Vanquish will try to infect it. So that's why it needs to hook some of these APIs. How many read the Frac 62 article by KDM? Okay, well, he said that Vice did not catch MT illusion, and he was exactly right. But he had an older version. I hadn't released the new version yet because Vice had a sort of a severe bug in it. And now that I fixed the bug, it completely catches MT illusion. So he and I have talked offline through email about that. And I think I put up a snapshot at rootkit.com, and I think he even said nice job. So that's sort of the state of a lot of rootkits that are publicly known about and contributed to. Some are even open source. Now we're going to go into another area, more insidious rootkit, FU, using DCOM methods. So customers are starting to demand more because their operating system isn't providing all the security that they need. They're looking to personal firewalls and host-based intrusion prevention systems. So HIDS/HIPS, HIDS being host-based IDS, HIPS host-based intrusion prevention systems, they try to detect or prevent processes from running, certain files from being created, possibly device drivers from loading, privilege escalation, and network connections being made outbound for the most part. So, but in a lot of cases, they trust the underlying operating system to detect or to report when these activities occur. So if you can compromise the operating system itself, in many cases you can obviously compromise the HIPS. HIPS uses things like, they can query the kernel just like any other application to say, like Taskman does, etc. They can hook userland API functions to try to get into the code path. They can hook the system call table also to try to get into the code path. Any HIPs or HIDs that you've seen that do registry, they monitor the registry access. They have to hook the system call table. There's about 9 functions in there they're looking for. Also within the Windows kernel, it's pretty advanced. You can register a callback for every single thread that's created. So before the thread fully gets established, your function will get called, and then you could take whatever preventative measures or so forth you want to do there. You can also register callbacks for things like image getting loaded into memory or process creation. So some of the problems is you have to be in the HIPS has to be in the execution path to allow or deny access. And these hooks look exactly like a typical rootkit. There's really only the difference is why they're there. They're there to protect instead of hide. But I say, who says we have to use an API to implement our rootkit? If you don't use an API, then any functions that the kernel's filtering on or has ACLs around, you can still achieve the same results without going through those functions. Also, if your HIPS or so forth has a problem with it where you can load a device driver even though they try to prevent you from doing that, then you can circumvent all their API protections. So the current design of operating systems, anyone who's taken a basic class has probably seen this before. There's 4 rings. The kernel and other third-party device drivers run at ring 0. Applications run at ring 3. Intel has a total of 4 privilege rings, but no one, for the most part, seems to use the other 2. This is not just Microsoft bashing. This is every OS. Seems pretty much, except maybe the really secure ones that I haven't seen that are rated by some federal agency as a level of confidence for security. So since there's only 2 privilege levels, there's no separation of powers between a third-party device driver or a loadable kernel module. Therefore, your rootkit can modify any memory that the kernel can also modify. That's what I do with DCOM. It stands for Direct Kernel Object Manipulation, a little play on letters there. So you have to be sort of really careful when you just start modifying memory directly, because you have to understand the underlying structures in a great level of detail before you do. Otherwise, when the kernel tries to use the structures, it will blue screen the box. So recall that the goal of the rootkit is to hide things, and we'll talk about what you can use DCOM to hide. So you can't use DCOM for every application of a rootkit that you may want to do. If you want to hide something on the file system, DCOM is not the way to go, because there's not an object in memory representing every single file on disk. Obviously, that's contained on the disk directory structure. Also, I'm sure there's other examples that you wouldn't use DCOM for, but you can use it for any of the counting mechanisms within the kernel for the most part. So you can hide processes, add privileges to tokens, add groups to tokens, manipulate a token to fool most forensics that are out there. There are some very advanced forensic tools that will catch DCOM type of issues. We had some of the students in our class who were from NCASE, and they're wise to these tricks. You can also use DCOM to hide ports. So everyone knows implication of hidden processes. To hide a process in Windows, here's how you would go about it. This box up top represents the kernel processor control block. It contains 3 useful pointers: pointer to the current thread, pointer to the next thread, and a pointer to the idle thread. These, once you get to this processor control block, which is simple to do, you can always find the currently running thread on the system. You follow that, that's in the E thread. E stands for executive and K stands for kernel. That's how Windows, in the operating system, that's how they name these objects. They're not an object in the C++ sense of the word. They're mainly structures. And they vary from OS to OS. So within an E thread is a K thread, and within a K thread, you can find the underlying process block represented by E process. And there's this linked list notation here where all the processes, all the active processes are linked together. Active is a bit of a misnomer. It's how Microsoft names the list, but just because it's marked as active doesn't mean it's not blocked or paged out or whatever. It just means it's a process on the system, so it'll be in this list. So to hide a process, you locate the processor control block. I have the address there. It's been in several books. It's hard-coded, you can always use that. If you don't like that methodology, because it may have changed, I haven't looked at 2003 or even XP, but doesn't matter because you can always use the FS register to find the processor control block and to find your current thread. The FS register contains different things depending on if you're in user land or if you're in kernel mode. A lot of people use the FS register in shellcode to find the process environment block. In kernel, it doesn't lead you to the process environment block. So again, once we found the E thread, we can go to the K thread to the eProcess structure. eProc contains list, and it's circular and doubly linked to how to process. It's pretty simple. We just change the process in front of us to point to the process behind us, and we change the process behind us to point to the process in front of us. And I'll demonstrate this. So in this example, we're trying to hide the currently running process, which would be this eProcess block. We have a blank. In the list entries contained a member called blank that points backwards to the eProcess block behind us, or behind the eProcess that we're currently at. And the flink points forward. So it's a forward link, backward link. So here we just changed the flink of the process behind us to point to the process in front of us. And we'll change the process in front of us to point to the process behind us. With those simple, I think I can get it down to, just two lines of C code, then we're completely hidden. So at first when I did this, I thought the process should freeze, but it continued to run, and that was somewhat of a mystery. And it turns out that the Windows scheduling is very advanced, and it's done on a thread basis. So even though the operating system reports on a process basis, it schedules on a thread basis. So there's a bit of a mismatch there. They should always report on how they schedule. That way this trick wouldn't work. Now, I'm not a Linux kernel guy by any means, but I have written a few LKMs. This was done about 2 years ago with whatever version of Linux kernel was popular then. I think it was early versions 2.4 or something. So Linux, you can pull the same trick off, more or less. You have to do a little bit of a modification at the end, but they have a task struct that represents every process. So it's just like an eProcess block. There's two pointers that are of interest, the previous task and the next task. They're just like our flink and blink within the eProcess structure in Windows. Then they also have two other pointers that we'll see why they're important in a moment, called previous run and next run. So to how to process, you go into its task struct and you modify the previous task and the next task to point around you. You just leave next run and previous run alone. Here's a representation of the list of task structs in memory. They're all linked together. But when we go to hide, here the parent process, or the first process on the system, is the init process. It has ID of 0 or PID of 0, and it has no parent. So its parent pointer in the task struct is null because it is the first process, or the first task. To hide this process, we're hiding PID 1901, and we have to change the init process to point to our hidden task struct on Linux. And I'll explain why. Because if you don't change the scheduler at all on Linux, your process freezes. And the reason this is true is because the Linux scheduler, I'm not sure how it is in the newer version with the more advanced threading model, but in this version that I was looking at the time, the Linux scheduler was walking the list in previous task and next task. Every time it'd see a task, it would update a goodness value. It would calculate a goodness value for that process, and based upon the goodness value ranking that you got, it would then schedule you a certain amount of time or jiffies on the CPU to run and put you in the appropriate place in the queue in the previous run and next run queue. So if you removed yourself from the previous task and next task, you never got the goodness value assigned to yourself, and you never got jiffies, so you never ran. So now we're going to switch gears a little bit. We're going to talk about some of the problems that can occur in modifying these lists. These lists are obviously private to the kernel. They do not export the list. They do not export the mutexes to the list. And if you're on a multi-CPU machine, obviously modifying this list can be very dangerous. Also, just in a regular threaded machine, if you're changing the list of any of these things, you could get swapped out. A pointer could become invalid that you've already saved off. You get paged or scheduled again to run, and you dereference that pointer and you blue screen the box. So in order to maintain synchronization, you either have to find the mutex that the kernel doesn't export to you, or you have to try to raise the Urkel level in your driver to dispatch level, which will stop you from getting scheduled out, or stop anyone else from getting scheduled in. However, that solution, you have to do it across every single CPU on the system because Urkel's levels are CPU specific. So just because one CPU is in dispatch state, the other CPU may not be. So here's a list of of the names of the mutexes in the Windows kernel to modify the list of loaded device drivers or to modify the list of processes. They're on the slide. So since they're not exported, we could find these by hard coding them. However, they move around a lot, so that's probably not a very good solution. Also, we could search for a known pattern in memory. There's functions within the kernel that obviously have to use these mutexes to schedule threads or just swap threads in and so on and so forth, or add processes, I should say. So you could search for a known pattern within memory, and then you would locate the mutex. However, it's somewhat kludgy because you're going to have to do it for every single OS because the functions may change on a recompile of the kernel. So you have to be very careful and very meticulous in all the versions of the OS that you want your rootkit to run upon. So this FU has code now. I haven't released it yet. I have to integrate it with Sherry Sparks. She did the research into finding those known patterns. So I'll put that in FU soon and hopefully upload it to rootkit.com. So besides hiding processes, we also may want to elevate the privilege of our token or just manipulate the token a bit to appear like another user. This will make, if we appear as another user, it can be difficult for some forensics to be able to tell what truly happened on the box. For instance, if the administrator has detailed process tracking turned on in the Windows event viewer, every time a process is either created or destroyed, they can see that action happen, and it'll also log who did it. So if you've stolen someone's password, installed a rootkit, elevated privilege, or whatever, and you have netcat running, as Joe user, well, you just tipped off the sysadmin that something's up with the Joe user account because he probably shouldn't be running netcat. However, if you make it look like system did it, it's going to be a lot harder for him to knock on someone's door or to revoke the account because why is system spawning this? His immediate thought's going to be go to the list of services that are running on the box, try to figure out if anyone's running his system, and he'll think he's been compromised by buffer overflow. This could result in a couple weeks of him trying to figure out exactly what happened. So in order to modify a token, I'll explain a little bit about what's in a token. It has a static portion and a variable length portion. The static portion has things like session IDs, the list of users, the list of, I should say a pointer to the list of users or groups, pointer to the list of privileges, and also like privilege count, etc. So in the variable length portion of the token, you have all the privileges such as SE load, device driver, SE shutdown privilege, SE debug, so on and so forth. You also have the users and groups and the restricted SIDs. I won't talk about restricted SIDs. That was introduced new in 2000. I haven't seen a lot of processes that really use tokens with restricted SIDs. So it's sort of hard to manipulate a token because you can't just grow the token, in other words, add to the bottom of it, because you don't know what's there. So it could be a region of memory that's invalid. It could also be some other process's token that you could start stomping on, and that's not a good idea. You could allocate a new region of memory and copy the users and group SIDs to that new region of memory with your new privileges and so forth. However, turns out that when the system goes to create a child process, it knows certain things about the token that I haven't totally figured out yet, and it does some mathematical calculations on where the token is because it's trying to copy the parent token into the child process. And because of this mathematical calculation, just changing the pointers within the static region of the token will not work. You either just get garbage in the child process's token, or in the worst case, you can blue screen the box. So my approach was there's a lot of privileges that are within a token that aren't really all that useful because they're marked as disabled by default. So if I'm not using the privilege, then why do I need it in my token? It's just taking up space. So I'll discard all these privileges that I'm not using to make room for the SIDs or the new privileges I want to add. So we'll talk first about adding privileges to a token using the decom method. Every token is represented by a LUID and attribute structure. A LUID is a locally unique ID. The attribute is such as the privilege is enabled, the privilege is disabled, or the privilege is enabled by default. That's what's contained in the attribute, D word. So here's a graphical representation of a token. There's the static portion in gray. The red privileges are disabled and the blue ones are enabled. They're not ordered like that, but just for the purposes of this graphic, they're ordered by disabled and enabled. So if we want to add some new privileges, we have to first get rid of the disabled ones. So what I did was I just moved those up in memory because I want to keep those around. Now the gray box in the middle represents the free space. You can think of it as free space that we have to add new privileges. And I just sort of stomped those into memory there. And now our token has 2 new privileges. And it's properly aligned and so on and so forth, so that when that process creates a child process, it will inherit the token properly. Groups and attributes, or adding groups is a little bit more difficult because there's a table in the token. There's a table in the token of pointers to all the SIDs and then the SID attribute. So this is a SID that is required for the process, etc. However, the SIDs are variable length, and they're not actually in this table. They're at the bottom of the table, and they're pointed to by the PSID member of the SID and attribute structure. So if you're adding a SID, you have to patch up all the pointers in the SIDs in the token so that they point to the new SIDs. And I'll show you what I mean by that. So we just freed up the memory. We got rid of the SIDs that were there, and we're going to put them back. Here's the SID and attribute table coming back into memory. The orange colors were the ones that were there originally, so we want to replace those because we want to maintain the same the same privileges that we had, or the same groups that we had before, we just want to add new ones. So we changed the pointer to point to where the SID is now. Now a new SID and attribute structure comes into memory, and its new SID comes in, and we're all patched up. So this will add any group you want. You can specify, hey, add the system group to my CMD process, and then CMD has system. A lot of this is even functionality that's not exposed through the Windows GUI so much, because you're just writing the memory, so you can add any SID that you can track back to its binary representation, you can add. So I also mentioned that you can fake out the Windows Event Viewer using DCOM methodology. There's the auth ID or the session ID that we saw in the static portion of the token. If you change that to there's 3 or 4 that are static, that never change, they're actually declared in the Microsoft header file in the DDK, I believe. That one of them happens to be the system LUID. So you can add, when you log onto a machine, you hit Control-Alt-Delete, your session ID is supposed to be created uniquely there at that time. So the system LUID, you can just hard-code that into your token using the DCOM method. Or you can, in addition to that, you have to make the first SID in the table of SID and attributes, you have to make it the system SID or some other SID in order to become that person on the box. This wasn't entirely clear to me at first when I wrote the FU rootkit. I just changed the system LUID, or changed the auth ID or session ID to the system LUID, and half of the event viewer was faked out by it and the other half wasn't. So it's sort of just a halfway solution. I had to go back and figure out exactly how the Windows Event Viewer determined who the owner of the process was. And simply does that by looking at the first SID within the SID and group structure. So using this method, you can make anything appear to be someone else. However, there's a caveat here. You cannot just arbitrarily change that auth ID to someone who's not currently logged in. If you do that, Windows will eventually blue screen, because every so often it seems to look at that auth ID, and it'll blue screen with this really cool message. I forget what it is right now, but it more or less tells you that something's really screwed up in the security here, because the auth ID that corresponds to that user doesn't exist. There is no user with that auth ID. So that's a nice way to go down. So if you want to detect a hidden process that was using the DCOM method, what you could do is you could modify the swap context function that's in the kernel. I'm not sure if it's exported, I doubt it, but you can find it and modify it. What it's responsible for is putting threads, paging, or swapping one thread out in favor of another thread that's then to be executed. There's a project from Hunt and Brubaker, Microsoft Research sponsored it, and it's called Detours for Intercepting Win32 Binary Functions. You could apply the same technology, although it's for user mode apps, you could apply the same concepts in your kernel for swap context. So what you would do is you'd overwrite the beginning of swap context to jump to your detour function. Your detour function has a call into a trampoline function. The trampoline saved off the original bytes that got overwritten, and then at the end the trampoline will jump into the original function, which was swap context in this case. And then when swap context returns, it'll jump back into the detour function. So you could do filtering or sanity checking or whatever there. So what we recommend is patching swap context so that it looks at the E thread that's about to get scheduled and determines if it's appropriately linked. The EDI register, right at the beginning of swap context, the EDI register points to the thread that's coming into the kernel, and the ESI register points to the thread that's leaving the kernel. So if you use those tricks to follow from a K thread back to the E process, as we showed in the previous diagram, then you could determine if the process was appropriately linked, if it never admit its threads into the kernel to begin with, or never schedule it to run, I should say. There's other ways to detect it. Last year in Black Hat Vegas, Joanna Rakowska presented a presentation about a little bit about rootkits, and she had the FU rootkit in there, and she had a novel idea to how to detect it, and that was to look at all the thread queues that are on the system and determine if they point to a process that's hidden. So that was her approach. The only problem that I saw with it, and she agreed, was that these queue addresses had to be hard-coded, and they move around from version to version of the operating system. She has not ported it to XP, although there's a few people at rootkit.com who've tried to port it to XP and have had some problems with getting that to happen. It seems that XP has a few different thread queues that Windows 2000 did not, and Windows 2000 has a few that XP does not. So it's hard to find every single thread on the system at this point because it's totally undocumented. You just have to reverse engineer the kernel. If anybody wants to take up that project and contribute to rootkit.com, I'm sure there'll be a lot of people that'd be happy. I won't get into this too much. You can detect hidden processes in much the same way in Linux. You could use some kind of injecto library or so forth, except in the kernel, and then go back and check for the previous task and next task to make sure the task structures are appropriately linked. Now we're going to try to have a few demonstrations of the FU rootkit and see what happens. Okay, you can ask FU to list all the processes on the box. This is better than asking Task Manager, because if there's a rootkit on the box that's using hooking techniques, FU just walks the list of e-process blocks in memory, so it never asks any API what processes are running, so there's never a problem as far as filtering in that case. So unless they're using DCOM, you can see processes that are being hidden by filtering. That's just one nice thing that FU does. If you want to hide a process, you do FU-PH and then the PID number. And here I'm trying to hide the system process. If it goes away, you should see, obviously, it disappear from Task Manager. And if the box continues to run, then it was successful. So system is gone. System can't even see system. This can provide a few different problems if you're doing some K wait for single object and you're waiting on some things within the system process. This can have interesting results. This is Process Explorer from sysinternals. just going to use it. My cmd.exe is PID 316 there, and I'll show you the token. So down at the bottom, there's no system group within there. You see here that a lot of these privileges are disabled by default. There's in fact only 5 enabled privileges. So if I go to cmd.exe that's running here, try regedit 32, you'll see I don't have access to the security because I have to implicitly give myself access to that, or I have to be in the system group, which I'm not. So let's try to add the system group to my PID 316. Now if I type regedit, you'll see that the security key is no longer grayed out. So I do have the system group within my CMD process now, and that process spawned regedit, so it got properly inherited. We can look at the token. There you see there's only 5 privileges because I got rid of all the ones that were disabled. And at the bottom of my groups, there's now the system SID, or the system group. So that process is system. What else do we have? We can also now, in FU, I added a way to hide drivers. If you're running XP, or if you're running Windows 2000 Professional, we had a problem in the class. We found a bug in the way that I was finding the list of loaded device drivers. That's a really simple bug, and it will be fixed probably by the time my plane touches down. So just wait off till next week to download FU if you want to play with it. So FU can list and hide drivers. I didn't make a nice, I didn't display it in the command line window. I just used the debug view. So here, this is the list of all the drivers on the system, and FU found that by walking. It's similar to the eProcess struct. There's a module entry structure within the kernel that's linked with list entries, and you can just run around this list and look for whatever you want, and then de-link the object from the others. So if I want to hide like ipsec.sys, I go fu-phd ipsec.sys, and this is case sensitive, I believe. Now ipsec was below this VMware driver and above the USB store.sys. That'll be important. Or it's number 102. So if I list it again, hopefully at 102, yeah, it's not there anymore. So there's some that say, okay, well, we can detect FU because we can see its driver, but I made no attempt in the original version to hide the driver. And even now, like the default install does not try to hide the driver because FU is more of a research project than an actual full-blown rootkit. If you wanted to hide the file on disk, which is like, after FU was released, Symantec, within about 11 days, had a 14 or 15 page white paper on FU, and that was sort of cool. But the gentleman missed the point. Even in the README, it says I make no attempt to hide the driver, and he was looking for it in the list of drivers, and he was also looking at it on the file system. So it could hide itself in more ways, but I don't want to release all that.